In this video, we're going to derive the subtraction formula for cosine. That the cosine of alpha minus beta is equal to the cosine of alpha times the cosine of beta plus the sine of alpha times the sine of beta. We're going to do this a little differently than we've derived or verified other identities. We're going to use our unit circle definitions of our trig functions. In fact, I'm going to use these two different unit circles to be able to verify this identity. So I've started here by drawing two angles, a big angle called alpha and a little angle called beta. The size of alpha and beta don't matter, and it does not actually matter that alpha is in quadrant 2 or that beta is in quadrant 1. That's just a choice I've made. It won't affect the calculations we do. So to start off here, I want to point out that alpha minus beta is actually in this diagram. If I think about rotating the alpha, if I take beta away from it, I get this angle that's between the terminal side of beta and the terminal side of alpha. In fact, I see that I get that angle right there. Right, that is the angle alpha minus beta. So that angle that appears in this diagram, alpha minus beta, well, that angle is not particularly useful to think about to think about using my unit circle because it's not in standard position. So what I'm going to do is take this angle, alpha minus beta, and draw it over here in standard position. All right, well, this is a unit circle, so I know that's the point 1, 0 out there. And by the definition of cosine and sine, this is the angle alpha minus beta. By the definition of sine and cosine, I know this ordered pair out here is the cosine of alpha minus beta, comma the sine of alpha minus beta. Over here on my original unit circle, now here I know this ordered pair is the cosine of beta, comma the sine of beta, and this ordered pair at the top is the cosine of alpha, comma the sine of alpha. So I have 1, 2, 3, 4 points labeled. And to verify this identity, I'm actually going to think about the length of the line segment between these 2 points. Well, because that's the angle alpha minus beta, I can think about that being the line segment between those 2 points, which is the same length over here. So if I call this length D1 and this length D2, what I'm really saying is that D1 is equal to D2. That those are really the same length, the same line segment, just drawn in 2 different places, because it's really just the line segment connecting those 2 points on my unit circle across the top of this angle. So we'll pretend I drew a straight line that connected those dots, but I see that straight line just move from one picture to the other. We're going to use our distance formula to derive this identity. And so we remember that our distance formula is that the distance between 2 points is the square root of x2 minus x1 squared plus y2 minus y1 squared, all under that square root. Well, if I think about it, if d1 is equal to d2, then d1 squared is equal to d2 squared. So I could imagine squaring both sides of my distance formula, and that's just going to get rid of the square root. And it's going to save me one step here in a moment. All right, so let's think about d1 and see if we can write down what the square of d1 is. So we're thinking about the distance formula, but just without the square root. So let's see, x1 minus x2 is a cosine of alpha minus a cosine of beta. So cosine of alpha minus cosine of beta squared, plus sine of alpha minus the sine of beta squared. Over here in this triangle, I'm thinking about the length of d2 squared. So the cosine of alpha minus beta minus 1 squared plus the sine of alpha minus beta minus 0. So that's just the sine of alpha minus beta squared. So this equation is true because d1 is equal to d2, and now I want to simplify this equation. And what we'll end up with is the difference formula that we're trying to derive. So I just need to go through and square what needs to be squared. So on the right-hand side, cosine squared alpha minus 2 cosine alpha cosine beta. And that's the first time in my derivation I see something that's starting to look like the right-hand side of the identity I'm trying to verify. All right, and then finally plus cosine squared beta. Now I do the same thing on this binomial. Sine squared alpha minus 2 sine alpha sine beta. And again, I'm feeling good because I see an expression that kind of looks like something on that right-hand side. And then finally plus sine squared beta equals. All right, now we need to think about what's going on this right-hand side. I have one binomial expression to expand. So I have a cosine squared alpha minus beta minus 2 cosine alpha minus beta plus 1 plus sine squared of alpha minus beta. All right, so that's not fitting real well there, but I think I see everything that's going on. All right, let's look at the left-hand side. I have a cosine squared alpha plus a sine squared alpha, and that's equal to 1. I have a cosine squared beta plus a sine squared beta, and that's equal to 1. 1 and 1, of course, make 2. But then I have the 2 cosine alpha cosine beta minus 2 sine alpha sine beta still hanging out is equal to cosine squared of alpha minus beta plus sine squared of alpha minus beta is equal to 1. Plus that 1 minus 2 cosine of alpha minus beta. Well, if I just look at that equation, I think about subtracting 2 from both sides. That 2 is going to cancel with that 2. And that leaves me with minus 2 cosine of alpha cosine beta minus 2 sine alpha sine beta is equal to minus 2 cosine of alpha minus beta. And if I just divide everything by minus 2, I've arrived at cosine alpha cosine beta plus sine alpha sine beta is equal to the cosine of alpha minus beta. And we have verified the identity that we set out to verify. Because these two lengths are the same, the difference formula for cosine has to be true. And that's it for now.